So just to let people know what we're doing, we're looking at exercise number 7 in the book for section 2.2. And Nura has let P be 2 as a factor of N. And her key says Q is 3 as a factor of N. And R is that 6 is a factor of N, which is a perfect key, by the way. Good job with that. We have 2 statements, A and B, and our job is to write them formally and to make a truth table and discover if they're logically equivalent. And it's perfectly normal to think, hey, we just used truth tables for arguments. These must be arguments. But this is actually application 2 of truth tables, where we use truth tables to discover if 2 statement forms are logically equivalent. So this is actually material from both section 2.1 and 2.2 rolled in together into one problem. So Nura also looked up the order of operations, and an or have equal precedence. So if we had a statement form that involved both and an or, we have to use parentheses to indicate which gets evaluated first. The other time we have to use parentheses is in, for example, an expression like the biconditional definition, if P then Q, and if Q then P, because we don't want to use the order of operations there. We want to evaluate P implies Q first and Q implies P before we evaluate the and. So if we wrote this without the parentheses, we would be evaluating the Q and Q first, and that really wouldn't make good sense. So yes, we're going to make a truth table and use application 2 of truth tables, which is to discover if 2 statement forms are logically equivalent. How many rows do we need in our truth table when we have 3 statement variables, Nura?
8.
Yep. So what shall we put? We're going to have 8 rows. Oh, I've got it too long. And I usually put a little dash line between rows 4 and 5 just to settle my eye down, because my eye kind of wanders. So that's optional. What do we put under P?
Rows 1 to 4 are true.
Good. So true, 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 true. Nice.
Rows 5 to 8 are false.
Exactly. All right. What about under the Q?
Rows 1 and 2 are true.
Perfect.
3 and 4 are false.
Exactly.
5 and 6 are true.
Good job.
7 and 8 are false.
You got it. And under R?
We alternate true, false, starting with true.
Exactly. I think you could be my substitute teacher on this now. You've got this down perfectly. So we're going to work up to statement A by first making a column for P and Q. See what I mean? I don't want to try to do it all in one fell swoop. I just don't want to think that hard, if you know what I mean. And then we'll make the column for P and Q, quantity implies R. Does that make sense to you?
Yeah.
All right, so this is statement A. Then we'll need a column for not P, a column for not Q, a column for not R. And then we'll just OR those together. And we can probably OR those together all in one fell swoop, because can you state the rule that would tell us when is not P or not Q? Or wait a minute, is it or? It's not not R, is it? It's just R, isn't it?
Yes.
Okay, so we don't actually need not R. So I'm going to
Oh,
erase.
no, it is not. I have it down. It's not R. I think so.
Is it? Let me double check. Okay, so it says 2 is not a factor of n, or 3 is not a factor of n, or 6 is a factor of n. So we have it written down right. So this will just be R. Does that make sense?
Yes.
Okay, great. So we actually don't need that column for not R, because there is no not R involved. So I'm just going to erase that mistake, and we'll have the column for B. All right, let's do this. If we want, actually, you know what we could do? We could go on and write R here just to make our life a little easier, it doesn't hurt to write a column twice. You don't want to ever write a row twice, because if you write a row, twice, if you wrote true, true, false here, and then you wrote true, true, false again, you'd be missing one of the rows. But it doesn't hurt to repeat a column just so we have these three really close together so we can easily evaluate them ORed together. So what would go under not P? Let's just go in and do the easy ones first.
Not P, rows 1 through 4 are false.
Exactly.
Rows 5 through 8 are true.
Good night. Good job.
Not Q, rows 1 through 2 are false. Rows 3 through 4 are true. 5 through 6 is false.
Yep.
And 7 and 8 are true.
Exactly. All right. Now, what would you like to do first? Would you like to finish B, or would you like to move over and start building up to A? It's up to you.
Let's do B first.
Yeah. So what are we looking for in order for not P or not Q or R to be true? What has to happen with these three truth values?
So it's an or statement, so we don't need both of them to be true for it to be true. But if we're dealing with three values, do we need two truths at least?
That is a great question. Or will be true if one component is true. Because if you say it'll be true if two are true, it'll be true if all three are true, because it's the inclusive or, but one suffices to make an or statement true. If you say, I'm going to have a pizza, or I'm going to have a salad, or I'm going to have cheesecake for dinner, if you do any one of those three things, you've stated a true statement.
Oh,
You've also stated a true statement if you do two of those things, or even all three, because we're using the inclusive or, not the XOR.
okay.
If it's three statements anded together, what do you think the rule would be for three components anded together to be true?
All three have to be true.
Exactly. But for or, one component being true is sufficient, even if there are 100 of them ORed together. Does that make sense?
It does.
Great. Here we go. Tell me what to write. Row one.
Okay, row 1, not P or not Q
Or R. We have them all right here to look
or
at.
R. We have one true, R is true, so it's true.
That's correct. Row two.
All values are false, so it's false.
Exactly.
Not Q and R are true, so it's true. Not Q is true, so it's true.
Exactly. And look, P is true, not P, excuse me, is true in rows 5 through 7. And
So
that's,
it's all true.
yep, because we see the truths right here. We don't, and it's fine if there's some extra ones, but so look at this. That's interesting. There's only one false here. It's almost a tautology, not quite.
Ah,
Almost a tautology, but all of them would need to be true for it to be a tautology. So it's neither a contradiction nor a tautology. All right, let's fill out the column for P and Q. So we're looking at the first two columns.
true,
Good,
P and Q. True,
right?
false,
Exactly.
false,
Nice.
false. Yeah,
Yep,
they're all false, so
yep, because P is false. Got a bunch of falses. Now we're gonna, but that's kind of interesting because we know in statement A, P and Q is the hypothesis, isn't it?
yeah.
So when we have all these falses for the hypothesis, what do we know about the truth value of the if-then with a false hypothesis?
It's true by false hypothesis?
That's right. So all of these are going to be true right off the bat because we have false hypothesis. That makes it easy, right?
Yeah,
So
that's
all we
good.
really have to do now is look and see what happens in rows 1 and 2.
So, that's true.
Yeah, true implies true is
Uh-huh,
definitely
uh-huh.
true.
True implies false, that's false.
And look at that. Look at these two columns.
They're logically equivalent.
Yes, they are. And it's always good to write a sentence to explain how your truth table informs your answer. What would you like to write to explain how your truth table informs your conclusion that they are logically equivalent?
Expression A and expression B have the same values, the same truth values, so they
Yep,
are logically equivalent.
nicely done. And I'm going to add just a little phrase. They have the same truth values in each row. So they are logically equivalent. I'll just write it out for the purpose of the notes, but you don't have to if you don't want to. Nice. So that's our application 2 of truth tables. It helps us understand if two statements are really saying the same thing. This can be incredibly helpful. If you've made a flow chart or you have laid out kind of like a higher order program to do some task for a client, being able to check, because your program might be more efficient than what the client actually said. If you can break it down into an expression for what your program is doing and compare it with the expression that the client actually gave you in writing. And if you can prove that they say the same thing, then you can demonstrate to a client that, hey, mine is simpler, but it is doing what you asked me to do.
That's interesting.
It is. There's real use for this good stuff. Because a lot of times these expressions can be simplified into something simpler. And we'll see that in action when we work on circuits next week, because circuits can be logically equivalent too. But we sure don't want to build a circuit with 8 gates if we can build a circuit that does the same thing with 3 gates. It just doesn't make sense in terms of labor and raw materials to build a real big fancy circuit when a simpler one can do the same job.
That's very interesting.
I think so.
I went over the chapter, and there were a couple things that were a little confusing. I think they had to do with the implication. In the book, it said it's not a great idea to think of P arrow Q as P implies Q because then it assumes that you can deduce Q from P.
Can you show me exactly where it says that?
Uh, Let me see if I can
I
find it.
think the point they're trying to make is that Q can be true even if P isn't, right? Because if P, then Q will be true even if you don't have P. But in fact, if the author said you cannot deduce Q from P, that's not true if you know that if P, then Q is true. So
Oh,
I'd like to see where, so I'm going to share my screen and let's take a look if we can in the book and see if we can identify where you saw that. Let's back up a little bit to the uh, conditional.
I think it was I think it was conditional statements, the start of chapter 2.
All right. So when you make a logical inference or deduction, you reason from a hypothesis to a conclusion. If such and such is known, then something or other must be the case.
It was under the truth table. Um, Trying to see if I can remember where it
A
was.
conditional statement is true by virtue of the fact that its hypothesis is false, is often called vacuously true or true by default or true by false hypothesis. I'm surprised she doesn't have that in there still, but that's okay. Yeah, vacuously true. And that comes from set theory, and we'll talk about the idea of vacuously true.
If you scroll down, it's under the note.
It's
She
got to
talks
be
about,
because of the false hypothesis. All right. So was it what the philosopher said?
yes,
Okay,
yeah,
the philosopher. You want to read this part right here?
yeah, it. It
Oh, I didn't
says,
mean to do that. I didn't mean to do that. I accidentally touched. Okay. Yeah, well, read that to us.
the philosopher Willard Van Orman Quinn advises against using the phrase P implies Q to mean P arrow Q because the word implies suggests that Q can be logically deduced from P, and this is often not the case. Nonetheless, the phrase is used by many people, probably because it is a convenient replacement for the arrow symbol, and of course, in many cases, a conclusion can be deduced from a hypothesis even when the hypothesis is false.
Good. Um, I think that the point that Epp is trying to make with this quote is that people mistakenly think that Q can't be logically deduced any other way, right? That you have to have P to get Q. And I think that's what she's trying to say there, because if P then Q will be true even when P is false. But I disagree with this statement in that if we know that P is true, we can deduce Q. But so I actually think I think that there's a logical error, to be quite honest, in that statement. Q can be logically deduced from P, but Q might happen because of something else. In many cases, a conclusion can be deduced from a hypothesis, even when the hypothesis is false.
So in class, when you use the example of applying or going to a store and being offered a job, if you show up, then you don't show up, so you can't say that you weren't offered a job because you didn't meet the conditions.
Yes, that's right. The thing is, there's a inverse and there's a contrapositive and there's the converse. So let's see, is that example a little further along here?
Um, the inverse, and I think it's further.
Yeah. Yeah, that's an interesting example. Let's take a look at that. Yeah, inverse error and converse error are very, very common, but I saw that example a minute ago. Do you know what page it's
It
on?
might have been on at the page we were, but all the way up, it's at the start of the chapter.
Okay, let's see if we can find it.
Yeah, there it is,
Oh,
in the gray box. Suppose there
okay,
it is.
so you want to read that one?
Suppose you go to interview for a job at a store, and the owner of the store makes you the following promise. If you show up for work Monday morning, then you will get the job. Under what circumstances are you justified in saying the owner spoke falsely? That is, under what circumstances is the above sentence false? The answer is you do show up for work Monday morning and you do not get the job.
That's exactly right. If you do show up and don't get the job, then the owner stated something falsely. But it doesn't mean that if you don't show up for work Monday morning that you won't get the job. See, that's what we call inverse error. You see, we naturally, in our ordinary conversation, think that when someone says, if you show up for work Monday morning, then you'll get the job, to mean if you don't show up on Monday morning, then you won't get the job. But they are not logically equivalent, because if we call P, you show up for work Monday morning, and Q, then you'll get the job, the statement that the owner said was if P, then Q. But that doesn't mean that if not P, then not Q follows. That would be the inverse. If you don't show up on Monday, then you won't get the job. You see, that's the inverse of if P, then Q. And the inverse is not logically equivalent to the original. That's the point that they're trying to make there.
Wow. See, I automatically assumed that
Sure.
if, yeah,
Because that's the
okay.
way that we use ordinary English. We actually don't use ordinary English in a strictly logical way. And that's one of the things that you will hear, like on the news, if you listen to news, converse error and inverse error are rampant in the news. And it's because the way that we speak English and can comprehend English ordinarily is not strictly logical at all.
Oh.
I know, right? It's a shocker, but it's true.
So the inverse and the converse are logically equivalent, but the original and the contrapositive are also logically equivalent. But within the four groups, they are not logically equivalent.
That's right. The original is not logically equivalent to its inverse. So it is technically not the same thing to say, if you show up for work Monday morning, then you'll get the job. To say that that means if you don't show up for work Monday morning, you won't get the job. But again, we comprehend it that way, even though it's not logical.
Wow.
I know, right?
Thank you, Professor.
You're very welcome. Those are really interesting questions. I can tell that you are really putting the work in. I see Sunita's joined us. Hi, Sunita. You got off work and were able to make it here
Yeah,
for the office hour.
how are you?
Well, we are well. How are you?
I'm good. Yeah, I just get home and then I just join you. I'm
I'm
watching.
so glad you could. Sunita works very hard. You don't mind my saying that, do you, Sunita?
Oh, thank you. Thank you so much.
You work so hard. I'm going to stop sharing now. Do you have a question, Sunita?
Now for now, I don't have any question, but I just still asking and I'm just looking and watching.
Okay. Nura, do you have another question?
No.
Nura?
Um, I was originally gonna go because I asked my questions and I'm trying not to take up too much time, but I'm finding translating from so in the graded questions, there is a question that uses variables. X, I think it's
Is it
I
it's
can't
a
remember.
WebAssign or is it in?
Yes.
Okay, let's take a look in WebAssign. I've got, is it assignment for 2.2 or
Yes.
2.1?
I think it might be 2.1. I found 2.2 to be a little easier, and I don't know
Uh-huh.
if I'm relying on the truth tables too much, you
No.
know?
Um, it's kind of almost impossible to rely too much on truth tables because truth tables never lie. But 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 if translating to ordinary English is an issue, then it's good to practice um, going back and forth from English to symbolic, you know. So, do you know which one it was? Here's the first one. Here's the second question. Oh, it's got the answers. I need to view it as a student so we don't see the answers.
It was assignment 2. It's 2.2. I'm sorry.
That's
It's
fine.
2.2,
You're fine.
and
All right.
it's number 3.
Okay.
And it's just it's just an example of what I'm having trouble with. It's going from just straight symbols to English language and back.
Right. Because here they're giving us English language and we're trying to maybe go to symbolic form in order to make a correct translation to the negation or contrapositive or converse. It never hurts to make a key. So if you were
Oh,
going, yeah, making a key, it can be, no pun intended, it can be key to your success. So on number 3 in WebAssign, section 2.2 WebAssign, I'm just going to make some notes and then I'll show my paper again. The statement is, if X is non-negative, then X is positive or 0. That's actually the definition of non-negative. I can give you some tips on setting up a key. One tip for setting up a key is to set up the key for the positive statement, not for the negation of a statement. But for example, X is non-negative. You could say P is the statement X is non-negative, or you could say that P is the statement that X is negative, and then not P would be the statement X is non-negative. That can be helpful.
Which one do you recommend?
It's really 6 of one, half a dozen of the other. I tend to always make my keys in the affirmative,
Okay.
but you don't have to. Any way you slice it, eventually you're going to probably have to negate a negation. So we can do it both ways. We could do, key one and key two, and then we can go through it both ways and you can see which way you like better. So for key one, I'm just going to do everything in the affirmative. That's the way I usually do it. So the statement X is positive, I would just say that's the statement Q, rather than X is not positive being Q. See what I mean? And R would be X is 0. Okay. Now, if we do it that way, let's just go through some of these and let's see if we can write, formal statements, and then we can see how easy or hard it is to translate. The original, if we use this key, that P is that X is negative, how would we write the original in symbols?
We would negate P.
Yeah, not P, if not P.
Oh, I see. Not P, then Q or R.
That's right. And since the or gets executed before the arrow, we don't need parentheses, but I'll put them there, but we don't need them. Okay. Order of operations tells us this or and this not happened first, and then the if then would happen last. But it doesn't hurt to put parentheses.
When we're doing classwork or something that's going to be graded, would you prefer us leave out the parentheses if they're not needed?
I have no preference.
Okay.
I tend to use parentheses, but if you understand the order of operations, you can certainly omit them. I have absolutely no preference. Now, for the negation, what would the negation be?
We would have the negation symbol, and then we would put the entire expression in parentheses.
All right, that would be the first step.
Oh, I see.
But now we want to remember the rule for negating an if-then. So let's just recall. I'll use A's and B's so we don't get confused. The negation of A implies B is, do you remember what it means to say that A didn't imply B?
It was a arrow, not no. Oh no.
The negation of an if-then is not another if-then. That's the first thing you have to understand. The negation of an if-then statement is not going to be another arrow statement. It's an and statement. And this is something that really hangs students up. Remember what A implies B means. It means if A is true, then B definitely follows. It says nothing about what will or will not happen if A is not true. So the only way that that can fail is that if A happened, you went to work on Monday and you didn't get the job. Citing that example that you were talking about.
And see, it makes sense when you say it, but when I'm doing the work and I feel like there's a time limit, then I guess I just don't think logically fast enough.
You're going to have to memorize that one.
Okay.
Some things you just need to memorize until it becomes more natural. You will absorb it into your logical framework over time. I definitely hear what you're saying. And that is one of the reasons why it does give students fits, is because it isn't really intuitive until you've absorbed the fact that, for A implies B to fail, that means the hypothesis happened and the conclusion failed to follow. It's not if the hypothesis happened, then the conclusion failed to follow, because that would be true in rows 3 and 4, but the negation is only true in row 2, because that's the only row where A implies B is false. So the negation can only be true in the row where P is true and Q fails. That's row 2. The first variable is true and the second variable is false. That's the only time this is true, because that's the only time that A implies B is false. Does that make sense?
That does. Wow. That's really interesting.
I'm glad you think so. So let's apply that rule where now P is playing the role of the hypothesis A, and Q or R is playing the role of the conclusion B. All right, so let's distribute this not through here.
Not P.
The
Is
not
that?
does not apply to the
Oh,
hypothesis. The hypothesis happened. Oh, wait a minute. Wait a minute. The original was not P. I did not write this down right. I'm trying to negate the original, but I forgot the not P. You're right. The original is not P for the hypothesis.
oh.
My bad. Remember, this was the original. And when I put this not out front, I forgot to write that one there. So, hey, even an old pro can make a mistake. But you're right. The hypothesis of the original was not P. So we're going to write down not P. Sorry.
But not the arrow. We're not going to write the arrow.
Nope. We're going to write and. And then B is Q or R. So we're going to negate Q or R.
So does that become Q
Yes.
and R?
Yeah, almost. We also negate the components, so it becomes not Q and not R. Because when we distribute a not across an or, De Morgan's law says flip everything, negate each component, and flip an or to an and. If it was an and, we would flip it to an or.
I think I'm following along. You negated not P, and then you negated Q, or
I did
oh,
not touch not P.
okay.
That was the original hypothesis. Yeah, I had made a mistake. The original hypothesis was not P. We keep that.
Okay.
And we
But we did negate Q and R.
Q or R, yes, we negate the
And
conclusion. We just keep A exactly how it is, whether it's got a not in it or not,
oh,
and we negate B. And since B was compound, we then used De Morgan's law.
and you exchanged the arrow for the and symbol. That was part of the first negation.
You bet. That's exactly
Okay.
right. The negation of an if-then becomes an and statement.
I see.
And so, so now you can think, oh, it's pretty easy to see what this statement is going to be, because we're using P as X is non-negative, X is negative, and then not P is that X is non-negative. So this is X is non-negative and Q is not positive and Q is not 0.
I see.
And that's clearly false.
It's false?
It's non-negative. Okay, that means, so if it's non-negative and it's not positive and it's not 0 either.
Oh,
A number's got to either be negative or positive or zero. And this says a number is not negative and it's not positive and it's not zero. But that makes sense because the original statement is true. If X is non-negative, then that's exactly what it means to say X is positive or zero. That's what non-negative actually means by definition. So the original statement was true. It makes sense that the negation would be false.
Wow,
Because, right?
wow.
Right? They have opposite truth values. So when you get ready to write this, just be careful because we chose for this key one to use the statement P is that X is actually negative. So not P is that it's non-negative. So if you wanted, to write this, informally, when you're looking for the right answer there, it's X is non-negative. But we can go through it again with the other key in a minute, and you'll see. And X is not positive. We don't usually say non-positive, but you could. And X is not zero.
Wow.
And I don't need a comma here. It's not wrong, but we don't need one because it's all ands. So we don't need a comma. It's not like there's ands and ors in there. We just have ands, so we don't need any commas. Isn't that one of the choices?
Yes, I think so.
Yeah, let's take a peek.
Just watching you solve it this way is very helpful.
Making a key really is helpful. And see, a lot of times I don't have time to say every single little thing. That's why office hours are so great. But I will always do by example. And we've done a couple of examples where I've given a key, right, and asked you, to use the key. And now you get to make your own key. So the contrapositive is the next thing, right? So let's write the contrapositive formally, keeping in mind that our original is right here. So do you remember what the contrapositive is? Should we write the little rule here? If A implies B is the original, what's
The
the
contrapositive is not B implies not A.
Good.
For the
So
inverse, oh, I'm sorry.
yeah, you're fine. Go ahead.
For the inverse, converse, and contrapositive, we keep the if-then format?
Yes.
Okay.
The sisters are all implications. That's why I call them sisters. They have that in common. They're all if-then statements. They're all conditionals. So great. So our original, our curly A is not P. Our curly B is Q or R. So what would the contrapositive be in formal notation?
It would be P, not instead of not
Careful, no,
P.
you told me the right thing for contrapositive. It's
Oh, I see. It would be not parenthesis Q or R,
good.
arrow, not P.
Exactly. So we can simplify this. We can use De Morgan's law applied to the Q or R, and we can simplify not P. It's like not, who's there? P. All right. So how do we use De Morgan's law here?
We would say not Q or not, no, and, I'm sorry,
Good,
and
good. You're
not
fine.
R,
Good,
arrow,
good.
and then that becomes P.
Great. So now if we're going to write this informally to figure out what the sentence is, how would we read it? Keeping in mind what our key is. So if Q is that X is positive, what is not Q?
X is negative.
Not quite, because the negation of positive isn't that it's negative. The negation of positive is it's zero or negative. So it's best just to say X is not positive. That's a surefire thing. See what I mean?
Wow.
Because zero is neither positive or negative. This is
Oh.
actually kind of a lesson in that fact. This
Ah,
whole exercise is to remind, hey, there's more going on than positive and negative. There's another choice, 0.
it's really interesting.
I'm so glad you think so. And what would not R be?
Not X is not 0.
Yeah, if that's a safe bet and correct. Safe because it's correct. All right, great. So now if we're going to write this sentence, as an English sentence, what would you write?
X is non-negative.
Well, we've got this arrow, which honestly almost be easier if it was here and here, because then we would get a reminder right here that we're writing an if then. So if
Oh,
it
X is non-negative.
is, I see, not Q.
X is not positive. I'm
If
sorry.
you're fine. If X is not positive,
And X is not 0. Then X is negative.
and that's exactly true. This is the contrapositive. That is true. So is the original. If X is not positive and it's not 0, then it has to be negative because that's the only other choice. And the contrapositive tells us that.
Wow. That
Yeah, see how it starts to tie in together? It's logically equivalent to the original. My word 0 looks like Zorro. See if I can fix that. Now, would you like to go ahead and we can work through the inverse and the converse now? Or would you like to try using a key where we actually take X is non-negative as our P, in which case X is negative would be our not P?
um could we do that for maybe the converse or the inverse?
Oh yeah, that's a brilliant idea.
Or we could use the with the other key because it's I don't want to go over time.
Okay, so that's fine. It's okay to go over time. If you're willing, I'm willing. I think students will find that I'm in it to win it with you. So yeah, so let's just imagine, you know, setting up a key that we just kind of just take what's given at face value. Okay, so
Can I ask a short question? The
sure.
the bottom there is the X, then the X is negative. So there is a not P, right? So how there is like X is not negative? Oh, sorry.
Because we actually chose for that's what we're discussing because you weren't here. I don't know if you were here when we set this up, but the point is we're learning to make a key and I personally always make my keys in the affirmative. Like I don't say not positive would be Q. I would always let Q be it is positive and not Q be it's not positive. But same way with non-negative. Even though this says X is non-negative, I choose P to be the statement X is negative and then not P to be X is non-negative because I find that that's more natural for me.
Okay, so
If it's got non in it, I'm going to make that the not, whatever the variable is. And so, but you don't have to do it that way. So let's just look at this same question. If X is non-negative, because it is maybe more natural for students just to pick what's actually written to make the key. And you can get exactly the right answer. We're still going to get the right answer. The key is supposed to be a tool. It's not, and there's not just one way to do it. Okay, so here, if we make the key kind of naively and say, hey, I see the phrase X is non-negative, I'm going to make that my P. But then it's always kind of helpful to say, well, then that means not P is going to be the statement X is negative. It's okay, you can do it that way. And that's what we're exploring right now. Luckily, Q and R are both just in the affirmative already. So we only really have one. This is a really nicely thought out book, I think. I think she really thinks things through. X is not positive. Again, we don't say negative because that's not what it means to not be positive. And X is not 0. So why don't we try, we'll go ahead and write our original again now because we have a different symbolic representation for the original because we have a different key. So what is the original going to be written as using formal notation with this key?
It would be not, let's see, it would be P arrow Q or R.
That's right. And you actually technically do not need parentheses because the or needs to be evaluated before the if then, or you can put the parentheses. I can put them like that just to indicate it, you can do it or not. Now let's work on the converse. Let's write it formally. And let's just remember, if A implies B is the original, what is the format for the converse?
B implies A.
Yep. So what would our converse be formally?
Q or R implies P.
Exactly. All right, now let's go ahead and practice writing it informally using ordinary English, and we should still get the same answer that we would get if we used the other key.
X is positive.
Remember this if then tells us. Yeah, I
If.
know. It's right. You kind of have to look ahead before you can even start. Okay, if X is positive.
Or R is 0, or X, excuse me, is 0.
Good job.
Then X is non-negative.
Exactly. So, and when you're doing the converse, it's actually easier. Let's now do the inverse and see what happens. And you can, like I said, you can make an informed decision. What's the inverse if the original is curly A implies curly B?
Not A implies not B.
Nice. Okay, so we're going to write the inverse using the original.
Not P implies not Q, O, or R.
I'm doing it in 2 steps. The
Okay,
whole conclusion has to be negated. So I am doing it in 2 steps. But you, I think, are getting it so well that you know what this should translate to.
not Q and not R. But I have a
Exactly.
question.
Please.
Even if you didn't write the parentheses, you would still have to distribute the not, and you'd have to change the or to and.
Here we actually need the parentheses because if we didn't have the parentheses, the first operator that gets executed is the not. And if we didn't have parentheses here, that not would only be attached to the Q. This not would only be applied to the Q. We actually have to have parentheses here to override the fact that we usually evaluate the not before the or. So there's no choice. If I put it like this, there's no choice. Here, we no longer need the parentheses, but you could use them.
I see. So when we're working out problems where we're negating, we need to keep an eye out for what we're doing so we know where our parentheses should be.
Yeah, and that's why I'm generous with parentheses. It never hurts to have too many unless you put them in the wrong place. But I don't tend to have that issue. See, when it was just like this, we didn't need parentheses. But once we have the negation, we have to indicate that negation is being applied to this entire conclusion, not just to the Q.
I see.
Does that make sense?
Yeah. So
I
depending,
know, it's a lot. All right, so how
depend,
about informally? Let's go. We've got our key right here for our P's and Q's and our not P's and not Q's. So how would we write this sentence?
if X
Nice.
is negative, yeah,
If X is negative, nice job. Uh-huh.
then X is not positive and X is not 0.
And that makes,
It's really simple and clear when you get it written out like that.
Yes, it seems very clear.
oh, in fact, see, this is the first time we've looked at the converse and the inverse. You know, we've seen only so far, well, we've seen both, but we didn't realize it maybe. The converse and the inverse are actually also true. The converse and the original could have the same truth value. They could both be true, but they don't have to be. So here's an example where the original, the contrapositive, the converse, and the inverse are all true. So that's worth noting. We have learned the original is not necessarily the same truth value as the converse. And it's never going to be logically equivalent, but it turns out that our choice of the statements P, Q, and R are such that, here's the big but it is possible for both the original and the converse, and of course that means then the contrapositive and the inverse, to be true. It is possible that they all have the same truth value, but it doesn't always work out that way. The only way it works out, the reason it works out that way in this example is because the original statement is the actual definition of what it means to be non-negative. And believe it or not, even though we write definitions as if-thens, they actually also go the other way.
Wow, that's interesting.
So this is a nice example where all four of the logical statements had the same truth value. Now, it doesn't make the converse logically equivalent to the original, but it is possible for them to be both true. Let's just think about that. Let's take a look at what's really going on when we're talking about logical equivalence of these sisters and what's really going on underneath the surface. See, I'll call it the four sisters because we have P, Q, the original, which is like the original sister, and then the converse. Oops, what's the converse again?
Q implies P,
That's very good. It's good that you're learning those. What's the contrapositive?
not Q implies not P.
And the inverse.
Not P implies not Q.
Exactly right. And I'm going to make a little column over here for not P and not Q so that we don't have to think too hard. I just want to point out to you what's happening. When I say they're not logically equivalent, true, true, false, false, under P, true, true. No, what goes under Q? You tell me.
True, false.
Good. True, false. So not P would be what? False, false, true, true. And under not Q, false, true, false, true. See, the point is, when we're picking Q's and P's, and in this particular example, we had a Q, a P, and an R. There were 8 rows. We can substitute different statements into P and Q, and that's what this means. It means, hey, if we substitute a true statement in for P and a true statement in for Q, then P implies Q is going to be true. Q implies P is going to be true because now Q is the hypothesis and P is the conclusion, and true implies true is true. Not Q implies not P. Well, not Q is false, so this is true by false hypothesis. And oops, this should be not Q, not P. Did you notice that? Did I
I
put
did. I didn't get a chance
you
to
can
say
always
anything.
speak up because I'm going to make errors at this time of night. I'm going to make errors anyway. There's no excuse. It just happens. I'm old. But here, not P is the hypothesis and it's false. So this is true by false hypothesis. Look, in this row, all 4 of them are true. It is possible for them all 4 to be true. If the hypothesis and the conclusion are both true statements, all 4 of these sisters are going to be true. But the point is, when we're using letters to represent statements, okay, we have to take into consideration that maybe the statement P is true and the statement we're substituting in for Q is false. Because if that's the case, then P implies Q is false, but Q implies P is true by false hypothesis because Q is the hypothesis. Not Q implies not P is going to be false because we have a true hypothesis, not Q, followed by a false conclusion, not P. And not P implies not Q is going to be true. So if you plug in a true statement for P and a false statement for Q, they don't have the same truth value, but the contrapositive in the original will always have the same truth value in every row. And that's what we mean by logical equivalence. And the converse and the inverse will always have the same truth value in every row. That means no matter what you plug in for P and Q, no matter what their truth values, the converse and the inverse are always going to evaluate to the same value. But there are only certain circumstances under which all 4 evaluate to true. That happens when both the hypothesis and the conclusion statements that you're plugging in are true statements, or if the hypothesis and the conclusion are actually both false. And that's exactly what it takes to have a biconditional. Think about it. P if and only if Q, the rule for when that's true is that it's true if P and Q have the same truth value. It's also the anding together of P implies Q and Q implies P. And that's true, false, false, true. So the biconditional is telling us when P and Q have the same truth value. That happens in row 1, they're both true, everything is true. Or in row 4, when they're both false, but still all the 4 sisters have the same truth value. That's because when P and Q are both true, P if and only if Q is actually true.
That's really interesting. That makes perfect sense.
Oh, I'm so glad. Hey, yay, good. So just notice when P if and only if Q is true, all 4 sisters are true because P and Q have the same truth value exactly when P if and only if Q is true. And if P, if P implies Q and Q implies P have the same truth value, of course, so do their contrapositions. The inverse is the contrapositive of the converse, but we call it the inverse of the original. But these 2 are contrapositives of one another. That's why they're logically equivalent. Just like the original and its contrapositive are, by definition, contrapositives of one another. Like if this was the original, this would be its contrapositive. See what I mean? If the converse were your original, you switch everything around and negate everything, and you get its contrapositive, which is the inverse of the original. I'm sorry, I might have said a little too much.
I see what you mean by the converse. If that was the original, then the inverse would be its contrapositive.
Right. So we say they are contrapositions of one another. Contrapositives, no matter what the context, are always logically equivalent to one another. So if you didn't get the job, then you didn't go to work on Monday. Because that statement was, if you come to work Monday, then you get the job. That is the same thing as saying, if you didn't get the job, then you didn't come to work on Monday. And I can hear you thinking, but wait a minute, I thought we said it doesn't tell us what happens if we didn't come to work on Monday, right? That's what you're thinking. But that's not what the contrapositive says. It says, if you didn't get the job, then you didn't come to work on Monday. But it might be that you didn't come to work on Monday and you were a bad fit for the job. One of the conditions is you definitely didn't come to work on Monday, but there might have been other things that made you not get the job as well, you see.
I see. So because you didn't you didn't get the job, so you did not come to work Monday.
Right. But it's not saying that that's the only thing that happened as a, because you didn't get the job. It, if you didn't get the job, then you didn't come to work on Monday. That's not the converse that if you get the job, then you came to work on Monday. If you didn't get the job, you didn't come to work on Monday, but maybe also you didn't come to work on Monday because they told you don't bother because it's not a good job for you. I know it's confusing, but there is a really nice problem in WebAssign. Let me share. It's one of my favorite problems in WebAssign. I think it's the last one. Yeah. If compound X is boiling, then its temperature must be at least 150 degrees. Well, if it's not boiling,
Then its temperature has to be less than 150 degrees.
not necessarily. See, that's not what this says. It says what should happen if it is boiling. If it is boiling, then we know it's this hot. But if it's not boiling, it might be because the atmospheric pressure is so high it can't boil, and it doesn't have anything to do with this threshold of 150 degrees. See, the inverse is if compound X is not boiling, then its temperature is not at least 150 degrees centigrade. And we don't know that that's true just because we know that this is true. Because we can't be sure the inverse has the same truth value as the original. And the statement, if it's not boiling, then its temperature is not at least 150 degrees Celsius, is the inverse. We don't know that the inverse is true. All we know is the contrapositive has to be true, that if it's not at least 150 degrees, then it's definitely not boiling. But if it's not boiling, it might be that it's not boiling because the temperature is this high, but there's something else going on that we don't know about, like a really, really high atmospheric pressure that would keep the compound from being able to boil, because that also affects boiling point. In fact, boiling points are a measure of exactly the temperature that is required for something to change from liquid state to gaseous state under 1 atmospheric pressure.
So logical thinking it requires that we consider that unless we're absolutely certain of something, we can't say that it is.
That's correct. Because there can be other factors that we're not aware of.
So we can only rely on the contrapositive when
That's
it
right.
comes to, okay, to certainly knowing that something is not.
That's right. See, because listen, this may not be the whole story. It says if the compound X is boiling, then its temperature must be at least 150 degrees Celsius. It doesn't say anything about and 1 atmospheric pressure, but that's generally considered part of the story, even though it's not written here. So there can be other factors that are coming into play, but one of the necessary factors would be that it's hot enough. But it could be hot enough and some other thing is keeping it from boiling. And the only other thing I can think of, offhand, is atmospheric pressure. Because
So
those
the
are two
contra,
things.
so the contrapositive gives us enough information to know that it's not, that.
Yeah, because see, this is necessary. For the compound to boil, it has to be at least 150 degrees. And maybe other things have to be happening too, but right now, all we know is this is a necessary condition. So if
So
we
the
don't have this necessary condition, no matter what else is going on, we can't know that it's boiling.
so the
Now,
contra, oh, I'm sorry.
but I mean, this is logic in real life. It turns out, that everything is more complicated than just pure logic. But for programming, pure logic is going to be your best friend.
This was very informative.
I'm so glad. Sunita, have you thought of any questions before we wrap it up and I call it a night and go finish a really bad movie that I'm going to watch?
Yeah, I'm good now.
I'm so glad that you came in. And hey, you can email me if you have some questions.
Okay,
And
ma'am.
I'm actually amenable to doing like a Monday morning office hour from like 11 to 12 if somebody's got some last minute questions. I don't mean that you can always email and ask. What's the worst that could happen? I would say I'm sorry I cannot. But believe me, my first desire is to always be available as much as possible.
Thank you so much for that.
Okay.
Thank you, Professor. We really appreciate it.
I had a lot of fun. I very much enjoyed this office hour. So have a good night and I'll see you soon.
You too,
See
Professor. Good night.
Good night.
you, Super Bowl.
Yeah, thanks. You enjoy it too. It gives me something to talk about with my pop.
Okay.
He likes it, so I watch it so I can talk to him about it.
Yeah, thank you.
See
Bye. Have
you.
a
Bye.